Okay, so today we're going to talk about maximum and minimum values of a function within a given interval. There are two kinds of maximum values and minimum values. There are the local maximum and minimum values, as well as absolute maximum and minimum values. So if we take a function like this, and take a given interval right here, an absolute maximum and minimums will just be the point with the highest y values within the given interval. So in this case, in this interval, the absolute maximum value will be right here. So you can see it's slightly higher than this. And the absolute minimum will be the lowest value, which in this case is right here. And it's lower than anything else. Now the local maximum would be the point where the y value is larger than anything near it. So it would look like either a top of a hill or like this, which we will discuss later. In this case of this interval, and within this interval, the local maximum would be right here, and then the local minimum would be right here. Now a point can be both the local maximum and absolute maximum, as well as a point can be the local minimum and absolute minimum. So in this case, we have a point which is both the local minimum as well as absolute minimum. Now there's a theorem that says that if a function is continuous within a closed interval of a and b, then the function must have both a maximum and a minimum within that interval. So take this function. So this function has a maximum here and a minimum here. And take any other function, say this function right here. There's always going to be a maximum and a minimum. However, as I mentioned, it is not true unless the function is continuous. So if we have something like this within the interval of the dotted line, this will not be a maximum. Same applies for minimum. Say if we have something like this within this interval here. It's not continuous here. Thus, this cannot be the minimum. We also cannot have a minimum or maximum which goes to infinity. Say if we have a vertical asymptote right at the end of the interval right here. This cannot be the maximum because it's not a defined point. It's infinity, it goes up infinitely. Okay, so now we know what an absolute maximum and an absolute minimum, as well as a local maximum and local minimum is. How do we find it? Okay, so let's take a look at a different function. Say something like this. Okay, so from what we've just learned, we know that this, as well as this, these are local minimums. So if we take a look at these points, we can note that the tangent line at these points have a slope of 0. Now we also know about the derivative of a function, and that basically is just the slope. We also know that the same applies for the maximums. The tangent line at these points also have a slope of 0, which means the derivative at these points also equal to 0. And thus we can conclude that any point where the derivative of the function at point x equal to 0, then at point x, the derivative has either a local maximum or a local minimum. However, there's another circumstance where we can have a local maximum and minimum. Take a look at this function. So right here, as we've learned, we can't find the derivative, as at that point it is not differentiable due to a sharp turn. So then the derivative or equal to does not exist. However, we also know that this is a local maximum, as this point is higher in y value than anything near it. Thus, we can find these kinds of local maximum and minimums by finding all points of x where the derivative of the function equals does not exist. There's a theorem called the Fermat's theorem. Which basically says that if f prime of c, or the derivative of a function x, f at point c, exists, and it is a critical number, or that it is a local or minimum max at point c, then it has to be 0. So basically it just proves that either the local maximum and minimum either have to be equal to 0 or it doesn't exist. However, the theorem does not apply to functions like this, which at this point, although the tangent line has a slope of 0, it, as we can see, is not a local maximum. To the right of it, the y value is larger than this point. And now we know that in order to find the local maximum minimums, we find the point of x where the derivative of the function equals to does not exist or 0. And these points of x are called critical numbers. Okay, so now we know how to find the local maximum and minimums. How do we find the absolute maximum and minimums? As I noted earlier, the absolute maximum can be the local maximums, say in this interval here. This is the local maximum as well as the absolute maximum. Now, however, if we change the interval from here to here, all the way to here, this will no longer be the highest point, and it will be at the end point here. So there are two kinds of absolute maximum and minimums. There are the points of local maximum and minimums, or they could be the endpoints. Now to sum it all up, we can have a very clear procedure on how to find absolute maximum and minimum. Alright, first we find the critical points, which we know can either be the point at which the derivative of the function x at point equals to 0 or does not exist. So it could either be something like this or this. Now we want to know what's the y value for these local maximum and minimum so that we can compare them. So find the y values of the critical points, but plug it values into the original function, so finding f of c. Now, the third step, we know that on top of local maximum and minimums, absolute extremas could be the endpoints. So to find the y values of the endpoints, we find f of a and f of b. Now, the last step, to find which one of these points, the local maximums, the local minimums, the endpoints, to see which one's the biggest and which one's the smallest within the interval, which is the definition of an absolute maximum and minimum. So compare the results to see which is largest, which would be the absolute maximum, and smallest, which would be the absolute minimum. Okay, so now let's look at an example. So we have function equals cosine of x, and we want to find the absolute maximum and minimums within the interval -3 and 4. So let's follow the steps to find the absolute maximum and minimum. So first we find the critical points, where let's look at the derivative of function equals negative sine x. And now we know that the critical points are where the derivative equals to 0 or does not exist. And we know what the derivative is, however there is no point within the interval or anywhere where that is undefined. So now we set that equal to 0 to find the point at which the slope equals to 0. And that will be either 0 or pi. And that is within the given interval, actually the open interval, because you can't take the derivative of the endpoints. And now that's step 1. Now let's look at step 2. Find the y values of the critical points. So let's plug in 0 and pi into the original equation, so we kind of find the y values. That would give us 1, and function pi would give us -1. Step 3, find the y values of the endpoints, so that we can compare these points with the endpoints. So endpoint 1 is -3, so let's plug that in. And that gave me around, and plug in 4, which is the other endpoint. We will get around negative 0.65364. Those are approximate values. And now we compare all the y values to see which one is the highest, or the absolute maximum, and which one is the lowest, or the absolute minimum. So first off, we have f of 0 equals 1. Let's list them out really quick. We can see that at x value 0, it has the highest y value, and at x value of pi, it has the lowest y value of negative 1. Thus, we can conclude that the absolute maximum is at the point 0, 1, and the absolute minimum is at the point pi, negative 1. And there we go. Now we know how to find the absolute max and absolute min.